we'll talk regarding the color image processing, and these are the parts that we will review for this chapter. First, we'll talk regarding color fundamental, then color models like RGB, CMY, HSI, NST, SC, YCBCR, and SciLAB. And then pseudo color image processing and basic of full color image processing we will see in this chapter, along with some MATLAB coding and MATLAB activity that we will review in each part of the lecture. Today also on the second lecture, we have one talk from a student, which is the last one, very main one. And the student talks also will be over today officially. First, about the color fundamental, we must know that in 1663, the Isaac Newton discovered that when a beam of sunlight passed through the glass prism, the emerging beam is split into the spectrum of color. We can say that the time that human understand that we have the different color was this activity, or that was the main proof to know the spectrum of the color. As I show here, the color spectrum is seen by the white light through the prism. It's something that you can see. We have the range of the infrared and ultraviolet one, and the color that which is visible for human to see. The color that human and most animal perceive in an objective are determined by the nature of light reflection. On the other words, the color is nothing but the reflection of the uh, light by the color obstacle, something that I shown here in the image. And as an example, we can see the green object which reflect the wavelength is probably is in the range of the 500 to 570 nanometer, while observing most of the energy at the other wavelengths. Means that by the reflection in the object, an object will act as something like filter. We just pass the proper or some different range of the colors to the human's eye, and then you can understand the color. If we want to see the wavelengths of nano in the nanometer range, we can see this range of the color. The chromatic light spans the electromagnetic spectrum from the 400 to 700 nanometer, and as we saw, our visible range is around 6 to 7 million cones in each eyes, as we have. And here you can see the range of the ultraviolet, X-ray, gamma ray, infrared, radar, FMTV, shortwave, and AM, which it's splitted based on the uh, range of the wave, and the visible light is between the 400 to 700 nanometer, as I shown in the figure. It means that the other sides we will not see, or other word is that we are limited to the one band of the wave, uh, limited even to that, and beyond and after that also we cannot see the colors. That maybe we can call this as the limitation of the human eye. 6 to 7 million cones in the human eyes we can be divided into three principles of sensing of categorized. corresponding through the red, green, and blue. Uh, about 65% in red, 33% in green, and 2% in the blue. And you should know that the blue cones are most sensitive one. Maybe this red, green, blue will remind you something as RGB that we will talk later about this RGB section. Let us go ahead and see that after this principle, for the color, we should have some model. And the purpose of these is to facilitate the specification of the color in some form of a standard. Because if we want to talk regarding the visibility or even seeing the colors, we should have some model about it. And then we need some standard. That is why the models will come to picture. In sense, a color model is a specification of coordinate system and subspace within that system where each color is represented by the single points. And the most color model are oriented either towards the specific hardware or towards the application. It means that these models will come by the specific hardware or towards the application that they have. Let us see. Suppose the first model that we will talk, it's the combination of three color of red, green, and blue, which as you can see in this model, each of them has the uh, some domain or some frequency which is shown in the figure. Suppose the blue one, it's 445 nanometer, and the green one is 535, and red one is 575. As you can see, the range or working domain of the red and green is much more than blue. And these are the consoles in our human, which is responsible for the color vision. Something that you should know is that the absorption of the light by the red, green, and the blue uh, are performing the wavelength for us, and we can see the wavelength of them here. See the published blue range, blue, blue green, green, yellowish orange, reddish orange, and red. These are the wavelength that you can see. And this axis is regarding the absorption of the color and also the wavelength of them. Maybe we can call these as the basic concept of the RGB model. But this RGB model is nothing but the three primary color that we can see. And approximately 66 of these cones are sensitive to the red, 33 are to the green, and 6 to the blue, as I tell you before. An absorption curve for the different cones have been determined experimentally. For standardization, the CI, that was one standard which invented in 1931, these designated the red color, green, and the blue light as the three primary color. These are mixed to generate the other spectrum color. We can what we can say, it's not new for us, this RGB concept, because even we work with color pencil and also any coloring and combination of them. We know that if we combine them, we can generate and invent the new colors. Something that we should note that the CI standard is not quite consistent with the response curves of the consoles, and this is because curves are not available till 1965. Then after 1965, little with the uh, concept of the CI is developed more, and it has more meaning. Okay. About these primary colors, we should note that having these three specific primary wavelet or current for the purpose of something like standardization is not having the meaning that RGB components acting alone can generate all spectrum colors. And what we know as the primary has been widely misinterpreted to the mean that the three standard primaries, when mixed in the various intensity properties, can produce all visible color. Then we should remember that color with the intensity has the meaning, and then mixture of them will create the new colors for us. When the three primaries are fixed, we can approximate all the spectrum colors by mixing the primaries, usually through the subjective experiments also. Now let us see the combination of them. Suppose these are the primary colors and how we can combine them. Suppose the conjunction between the cyan, magenta, and yellow, with this we can have the white one, which is mainly it's the conjunction of the red and green and the blue, means that it's at the center, and then by the intensity which we can give them, we can have and mixture of the pigments, we can have the uh, other colors like this. Uh, then, if we want to look more close to this RGB model, this is based on the Cartesian coordinate. And we can assume as the red one as 1, 0, 0 for the RGB. It means that the value of the R is equal to 1. On the other corner, we have the green, which represented by the 0, 1, 0. And the other side is 0, 0, 1. I should note that exactly in the MATLAB also, if you want to implement the RGB colors, or maybe you want to difference the sheets, this sheet, you can use this concept which I will tell you when we start to work with the MATLAB. The color subspace of interest in the cube, in which RGB primary values all at the three corners, you can see, and black is at the origin. This point is the black, which obviously it should represent with the value of R, G, and B equal to the 0. And that is what we shown here as the 0, 0, 0. Okay. Then with respect to the other corner, we can have different colors, something like cyan, yellow, and also even white. We know it exactly as the opposite direction of the black, which all the RGB 1 are equal to 1. It's exactly matched to the RGB model and what we learned till now. Um, but mainly, if we want to talk about the color fundamental, the characteristics generally used to distinguish one color from others are split it into three parts. Means three main factor will generate the different color for us. First one is the brightness, which is the chromatic notion of intensity. Hue is the dominant wavelength in a mixture of the light waves and represent the dominant color as perceived by the observer. And saturation, which is relative the purity of the amount of the white light mixed with the hue. these are the three maybe factors that can be uh, bring a different color for us. Then if I wanted to show the red, green, and blue with denoted by the X, Y, Z, a color is defined by its trigonometric coefficient, which we can see as the X divided by X plus Y plus Z, and Y divided by the summation of them, and Z divided by all. These can be representing the X, Y, and Z. Okay, just 1 minute, please. Um, then, based on the CIE chromaticity diagram, as we shown, it shows the color composition as the function of X as the red, Y as the green, Z as the blue. We can have like this, and X-axis and Y-axis can be performed different color range for us. This is the maybe the diagram which shows the different color based on CIE one. But some point that again we can see that this cube, which is based on the 24 color of 20 bits of 4 color, and can be represent the RGB for us that we thought maybe, but now you can see with the 24 bits, and you will see the variety of the color there as it shows, and the pixel depth, which is the total number of the color that you can get. It's around 16,000, more than 60 billion, sorry, um, of the color that you can see there. It's come from the 2 rises by 8 rises by 3, or power by 3. And here you can see that how the RGB color is generated with the different value of the R, green, and blue, which can be uh, mixed in the color monitor section, and you can see the RGB one here. At the down also I shows when R is equal to 0, when G or the green one is equal to 0, and blue one is equal to 0. It can be the RGB parts, and the mixture of them will generate the RGB color for us. The valid values for the RGB components in the safe colors are shown here with the hex to the decimal and color equivalent to them. And the 260 safe RGB colors shown here that you can see, and all the grays in the 256 color RGB uh, are representing with this chart. The main aim of this chart is that to showing the different color with the range of the RGBs, and maybe the codes that we can relate them to them. Maybe I don't know how who is working. I think most of you may be working with the Photoshop and also color. In that each color has the name with which coded with the numbers. Suppose 266, 256, or 200 of the red one, it's exactly different than suppose another red. Maybe some of us we cannot distinguish between two reds correctly, but they have the difference code. Generally, people who are working with the pictures or the active with the color picture, they are much more thinking and also working for these parts. Again, here I shows the safe color cubes in the RGB that you can see the variety of the colors there. Okay, But if we want to summarize this RGB, we can say that RGB image can be viewed as the three different sheets or image, a red scale image, a green scale, and a blue one, which stacks on the top of each other. And when fed into the red, green, and the blue inputs of the color monitor, they produce a color image on the screen. An RGB image is sometimes referred to as a true color image, as the precision with which a real life image can be replicated has lead to the nickname, means the true color image one. In MATLAB also, RGB image is basically n by n by 3 array of color pixels, where each color pixel is associated with three values which correspond to the red, blue, and the green color components of the RGB image at a specific spatial location. So the color of any pixel is determined by the combination of the red, green, and the blue stored in each color planes at the pixel's location. Here you can see the m by n array, which specify the different color and how they are connected to each other. We will talk more about this MATLAB section and implementing then, but as you can see in the above pixels, suppose A, we have the value of 255, 0 and 255 here. It means that we have the red one and 0 for the green and the 255 for the blue one, which is determined by the combination of intensities, which is stored in the red color frame, green color, and the blue color. And here also, suppose we have 127, 255, and 0, which this combination at the other corner also can generate the different colors. RGB color image are shown with the m by n with the three-dimension array of color, as we say, and each color pixel is the triplet corresponding to the red color and the blue. An RGB image may be viewed as the stack of the three grayscale image, as you can see here. In MATLAB routine, CAT can be used to stack the three components of them. Even we have another methods that we will see later on the RGB section. The next model that we will go to talk is CMY or CMYK model, which is the primary color of RGB can be added to produce some secondary colors, which we call it red plus blue can generate the magenta, green plus blue can generate the cyan, and red and green one can generate the yellow one, as represented in this uh, color. That is why they call it CMYK. C uh, stand as the cyan one, M stand as the magenta, and Y as the yellow one, and as the model of CMY model. K is the cyan one. Here you can see the combination of the color of the RGB also come to picture, which can help us to have the more range and more meaning for the colors. This CMY colors space, it takes the cyan, magenta, and yellow as the primary colors, and CMY is widely used for painting and printing. Even maybe you will see again in the Photoshop uh, software that they will ask you about the CMY and RGB lights that you can generate them. The model that we can have for the CMY can be easily converted from Rgb model, and if you assume the Rgb as the matrix form, you can have the below matrix to convert to the Rgb colors also, but have the subtraction of the 1 1 1 in each rows and columns, and it will generate the CMY for you. As you can see, all the colors value have the normalized to the 0 to 1 range, then equal amount of the pigments primaries of cyan, magenta, and yellow can produce the black. And in practice, the combining the colors for printing procedure produce the muddy looking black, something like that. If we want to produce the true black, the predominant color in printing, the fourth color black is added given the rise to CMYK color model. Then CMY color space, it takes the colors as I said. And if suppose we want to convert from RGB to CMYK, we have one statement in MATLAB which we call it IM complements. And from that we can convert to the RGB color. What more we can say about this model is that theoretically speaking, equal amount of the pigment primaries of the cyan, magenta, and yellow should produce the black one, and in practice, such a method can generate the quite muddy black, as we said. Then, if we want to produce the true black, a fourth color of the black should be add and give rise to the CMYK colors. K means the black in K. Okay. Then now we understand why we have the CMYK1 in the model. Let us see CMY and CMYK, which in CMYK models, now we add the black color also to the image. See, on the left side, you have the CMY, and the right side, you have the CMYK. And you will see that little bit the colors are changed now. Change in the sense that the black one also come to pictures, and you can also have that range of the color in this model. The next model that we talk is HSI. The point in HSI is that human eye can distinguish one color from the other based on three parameters, as we say, hue, saturation, and brightness, which we say hue is the color that evoked by the signal wavelets of the light in the visible spectrum, or by relatively the narrow band of the wavelets. We represent dominant color as perceived by the observer. And next factor is the saturation or purity, which refer to the relative amounts of the white light mixed with the hue, and it's inversely proportional to the amount of the white light added. To desaturate a color of given intensity in the subtractive system, such as watercolor, one can add white, black, and gray. And the end one is the brightness, which is embodies the achromatic notion of the intensity. Maybe we can give the brief to these three parameters of the brightness, which is the achromatic uh, notion of the intensity, hue as the dominant wavelets in the mixture of the light waves represent the dominant color as the perceived by an observer, and saturation, which is relative purity or amount of the white light mixed with its hue. Then hue and saturation together are chromacity, and for any particular color, the amount of red, green, and blue needed to form it, we can call it 3 stimulus, and uh, they are can be denoted as the X, Y, and Z. What will be changed here? This is the this term will be added, which is the summation of the X, Y, and Z, and now we assume it as the one. The difference now between this and the RGB one is exactly this new term that you can see here. Okay, here also this is the CIE chromatic diagram based on the HSI model, which you can see here. It's a function of X as the red, Y as the green, and Z can be determined as the Y minus X minus 1, Y. And again, you will see the range of the color which we can have in these uh, model. Something that we should know on CIE chromatic diagram is that any color which is located on the binary of the chromaticity chart is fully saturated, and any points not on the boundary but within the diagram represents some mixture of spectrum colors. The points of equal energy represent the standard white light. Its saturation is 0. As a point leaves the boundaries and approaches the point of the equal energy, more white light is added to the color and it's become less saturated. A straight line segment joining any 2 points in the diagram defines all the different color variation that can be obtained by combining these two colors additively. Next model, sorry, before talking about the next model, we will see a little bit more about this HSE model, which is used three measure of description of the colors of hue and saturation and intensity, and the relationship can be represented in the cylindrical coordinate system, not in the Cartesian against the RGB one. Angle around the central vertical axis correspond to hue. Distance from the axis correspond to the saturation, and distance along the axis correspond to the value that you can see now. This HSI model that you can see them as the sheets of the white, green, and the blue, and illustration of them which we represent here. Here also I shows the HIS model, which is the conceptual relation between the RGB and HSI, as you will see. The white, black, blue, cyan, yellow, red, and green are shown here, and the different representation uh, between the RGB and that now come to pictures. Now, what you can see, or the aim of this figure is that it shows the hue and saturation in HSI as the H of the hue, S as the saturation, I is the intensity, and the dot is then our arbitrary colors of the point here, this dot. What we have one angle from the red axis, which is given the hue, and the length of the vector is the saturation, and the intensity of all color in any this plane is given by the position of the plane on the vertical intensity axis. This figure is it's nearly the same as the previous one. What we should know now is that how we can convert now the color from RGB to HSI. Suppose give an image in the RGB format. The H components of each RGB can be obtained by this formula. We have theta or 360 minus theta if B is less than G and if B is greater than G. And theta value will come from this formula that we have in HSI systems. More, if you want to see the now conversion from RGB to HIS or HSI model, you will see that we need the S factor, which can be generated by this formula, and I, which can be the average of the value of R, G, and B, and S can be the formula that we have at the top. Then simply, if I want to take the HSI to RGB, we can have the formula of the RG sectors from this formula. Again here, but the difference is that when H is between 0 to 120, the formula is this. When H is between 120 to 240, we can have H and R and G as the mentioned uh, parameter in this slide. And if H is greater than 240 and less than 360, we can have this. Then what we understand, uh, we have three formula to convert from now HSI to RGB, which it depends on the value of the H. Here I show the RGB image and the components of its corresponding HSI. Pictures B is the hue, C is the saturation, and D is the intensity which we have here. The next model that we will see is NTSC1, which is the National Television Standard Committee as the full form. And it's the color system which is used previously in the analog television. Now, that type of standard is not more in use. But in this model or in this space, we have the grayscale information which is separated from the color data. And what we have here, the same signal can be used for both color and the monochrome TV sets. Image data, as you will see here in this model, consists of three components of the luminance, which we shows with the Y, hue, which shows with the I, and saturation, which shows with the Q. Um, let's talk more about this model, which now, suppose if we want to do the conversion between the RGB and YIQ for this NTC model, we can have this matrix formula with this coefficient, uh, which with the statement of RGB to gray, we can simply do it in the MATLAB, but it's really this matrix which hand over the jobs and doing the jobs for of them. Then if we want to see briefly, if we want to convert from RGB to YIQ, we can use RGB to NTC function, or YIQ to RGB, we can use NTC to RGB, which we will see later on MATLAB implementation parts of today. One more model we can have. Actually, we can have two more models, but we will see one before finishing the first part of today. This is Ycbr model uh, color space, which is extensively used in the digital video. And in this model, luminance is represented by the single components of the Y. Color information will be stored as the two color difference of the CB and CR. CB is the difference between the blue components and reference value, and CR is the difference between the red components and the reference value as we have. Then the RGB to YCBR, it's the conversion will be this formula or this matrix form, which in the MATLABs from RGB to YCBR is based on RGB to YCBR, and YCBR to RGB can be implemented by YCBR to RGB MATLAB function. We can use them, but really this is the act of this matrix on RGB plus some coefficient, which will be add and can generate this conversion for us. The um, last model for the color is CIE lab that because we have now little bit at the end of first part of today, I will talk in the second part of today lecture about these models, and after that we will go for the uh, implementation of these models in the MATLAB. We have some example that we will see in the next part of the today lecture. Yes. Next is that the coordination for this model is based on the below formula that I give you here, which in that we know the coordination are computed from X, Y, and Z values as the uh, following formula that we give. L is equal to 116 F by Y divided by 1n minus 16 A, also with some coefficient, and B also, where we can say that we have the T and the uh, we have the T powered by 1 by 3 if T is greater than 6 divided by 29 powered by 3, and also uh, in the other case, it has the second formula that we give here. Here, Xn, Yn, and Zn are the CIE XYZ transmissilus values of the reference. White point, which is the subscript of the n, suggests the normalized one. Um, More if we want to know about this CI lab, which we can simply implement it with the make C forms and apply C forms syntax in the MATLABs. There is one example here that I prefer that we see it in the MATLAB section part, and which it's exactly the we can see the performance. Okay, till now we review all the color image model which is available till now. Maybe the famous one. We cannot say the available. Maybe tomorrow one person generate one new model. But till now, whatever we know, we reviewed them. But as the aim of our course, which is more working on the MATLAB, I bring the brief um, function which we need uh, to work if we want to move between the models. Suppose from RGB to HSV, HSV to CIE, 19067 LAB, suppose RGB to CIE 19031. All the models, all the famous models, conversion formula are here. This is in tables, and which I take from MATLAB help. You can easily take it, and it's available there. But now, let us do some work on the image. If you are agree, we can do that before. Yes, Mohammed Azmin, come and talk for us. Mm, I think, let me share my screen for you, that you also can see my MATLAB environment, and by that we will see some formula. Can you please see my desktop? Just hold on for 1 or 2 minutes.
It's coming, sir.
Okay, it's coming. Good. Thank you, Kyle. Let us start from separating the sheets for the RGB. What we learned was that in RGB we have three different sheets, yes? R, G, and B, red, green, and blue. If suppose I have one image and I want to access just the green levels of them, or green or blue or red one, what should I do? Okay, let us see. First three lines are common, CLC, closer, and clearer, that you know the aim. Second is that I will read the image and then show the image. What image I use this paper image, which in that you know that the variety of the colors are more. Let us first show that. This MATLAB is busy. Yes, it's come. This is my image, my original image. Now what I want to do, I want to separate the colors in that. As you remember, I give you one concept. The concept, if you remember, for the coordination was like that, that if I give the 0 value to first part of this matrix, it means that I will delete the red components. If I give the 0 to the second value, it means that I will remove the green value. If I give the 0 to the third value, I will give the 0 value to the blue part. How I can do that? Simply see this part just then. See, if I put this matrix from the reading image, it shows me the red one. If I put this as 2, it will shows me the green one. And if I put it as the 3, it will show me the blue one. For the first step, what I have done, I remove green, blue as and also from the original image, and just I show the red one. Let us see, is it work or not? Yes. I don't know. Is it visible?
Yes,
Now
sir.
it should be better, maybe.
Yes, sir.
Yeah. Here, what I have done, I just extract or put the colors from the sheet of the red. But here also, you will see the different red. See, lighter one and darker one. Huh? And even this one is also more light than the downside here. You will see, whatever I will see, I will just see the red one. The same if I want to work just for the, suppose, for the green one. I can do the same here. Yes. And if I want to put for the blue one also, I will take the 0 value to that. I will run the program again. Then you can see the three different sheets separately there. Yes. Just green one, just blue one, and just red one image. which represent the RGB for us. And what I wanted, you mentioned that you will see the different color between 0 to 255, suppose of the red or green or the blue in each separated sheet. That was the first job. What about the next? The next example, we will go to convert from RGB to HSV model. Let us see how I have done that. Same photo papers we will work, and RGB to HSV is the conversion, which by that you can convert it to HSV, and then you can change the hue of that and make the show the range and uh, regenerate the HSV image here and then back to the RGB. I mean that first I will convert the RGB to HSV, then from HSV I will come back to the RGB model once more. Let us see the result. Yes, result is like that. In HSV, you will see the hue and intensity and brightness there. And then from conversion of HSV to the RGB, you will see some image are corrupt. See, this red one, please see. Yellow one, you will see. It's not like the original RGB, but it's near. Okay. It means that if we convert, maybe some specification will gone, which we cannot reconstruct. There is some method that you can do it. Okay. But now, till this time, I will not think for how to have the correct one. Maybe later we will talk how to correct this one. The example number 3 is the example which we will going to the convert the RGB to YCBCR. Yes. And I should tell you that each model has its application. Don't forget. First, I read the RGB from one another image of thief because Roy also tell me last time he needs some others input for the image. This time I try to work on some different image. Then we have the RGB to CBCR, which is the function, and convert the RGB to CBCR. Then I show it, the original one as well as CBCR model. Let us see. Yes. Yes, this is the difference between the RGB one as well as YCBCR here. It shows the mm, one circuit diagrams here, which based on now the feature and also the next application, we can say that this image is good or bad. Now we cannot say that it's bad or it's good. Okay, consider this point, which is the application of the next one. Again, RGB to CBCR with one more photo from the jungle and that which I bring. Let me see the time also that. Okay, same function we use to convert. Yes, this is what we can get as the output. Index image with RGB and index with the YCBCR. You will see that most of the colors are gone and just red and some green one and some small blue are remain. Rest of them are gone. Uh, the next things or next example, which here we will see from RGB to NTSC or YIQ, how we should convert. As we say that there is some matrix constant and formula for converting from RGB to YIQ. For the Y, we have this formula. For the I, we have next and Q are mentioned here. And we implement the formulas here inside our MATLAB code. Purposefully, I put the theoretical parts here that you can read it also and understand better the matrix form that we showed. Let us see and run this code. Yes. This is the NTSC, which as it's used in the analog uh, TVs later, means that around 20 years or 15 years back, and now mainly it's not using. Now you will see the original image and YIQ image. It's shown here, and now you will get the difference between RGB and other one. Okay, next example. It's about yes, this one. This is again RGB to NTSC, and also getting the value of the I, which is equal to the gray color. Yes, let me copy paste. Let us run it. Yes, original image, YIQ image, and also NTSC1, which are represent in this image, and you can get the difference between RGB and the final product of the code again here. Okay, and now RGB to CIE model that we talk about that model at the uh, initial of this today lecture. Okay, let me, yes. Now let us run it. Let's go ahead. Original image as the RGB and CIE LAB model, which represent here. Okay, the next one, conversion, which is a little bit big code. I should share. I think Kaya remind me to share this code for you to
Okay,
understand it
sir.
better. Okay, and this code is little bit big, but that was what I found to read the concept of the RGB. This is not much more what we can say high-tech code or very fabulous codes. It's okay, but anyway, to review this concept of the model and have the information about the difference will help you. There is one little bit long code that I shared it in Dingtalk. You can download it now. It's about conversion between the models, means that color model. I want as the task, you run this code and also uh, note down about the algorithm and the parts. I think just this code is enough, but if you want, you can also work on the what we can say other codes. If you send just one or so, I don't have problem. But because you should send the MD lectures, I understand that. But what I want that you know, run the MATLAB code that I share on group and write the note about result. What I mean that after running that, you have some figure number one, what it will shows and why it's showing this number. What the difference between this v value image and the v value is 0.95. On the other sides, for the other figure also, you will see the different value of the v, what it will shows. And in figure number 3, here, you will see the different value of the L. I put enough description inside the files. If you see these, generally I try to, when I will bring the code for you, I put some comment also inside of that. You will see that how we will do the coding, and there is some description that you can read it. I shared this as the task. You should run this and give the note. Little bit analyze this program, how it will work, what is the result, what is the output, and why that results come to picture. Understand?